phase regression and do multiple regression. And we'll talk about the tests we make in a sense the rest of the topics, or many of the remaining topics. The last time we talked about the regression summary, right? And that we get a standard error, so we can do the t-test of beta 1 equals 0, or we could do confidence. Okay? And that'll remain true for the multiple regression. There's another test that I want to talk a little bit about because it's the basis of the other test we're going to be talking about. So there's a second test. Beta 1 equals 0. And if you go back to, we started regression, we had this function. That's the thing we minimized, right, to get to our estimate. And it's a dispersion function. It is an estimate of scale, right? And if you standardize it the right way, if you have a normal population, it will if you look at this dispersion function, this would be the reduced model. Okay, so that would be, this would be the full model. Okay, the reduced model is the full model. Subjectation. So of course it would be this, right? With no x in it. And then if you were going to look at the dispersion function for the reduced model, there's no x. So it's just be 0. But this will still have a value, okay? And actually it's an estimate of scale, it doesn't look like it, but if you standardize it the right way at the normal population, okay, for a normal sample, it'll be a consistent estimate of say, population standard deviation. So this is the amount, we talked about this is the amount of dispersion left, right? After you fit this reduced model. And then you fit the full model. And then the dispersion left. And it's d of beta happens. Okay. So the reduction in dispersion is just b of 0 minus b of 0. And this was the numerator of the R coefficient determination we talked about. Okay, so large values of RD indicate gauge survey, right, you've accounted for much more dispersion. First of all, RD small indicates it's not, right? They're about the same. This one will always be a little bit bigger than this one. So we simply reject H naught if RD is too big. Okay? So there's our second test, and then we just have to standardize it. And standardization is given in the text. It's just, I call it an F statistic. And it's just going to be, there's a 1 in here, a 1 constraint. So the 1 constraint in the hypothesis. That'll change. And then downstairs you have tau aggregators. And then you compare this with that critical values with 1 and usually n minus 2. Okay. So there's a second test, and this test will be using a good bit. And we can calculate it in Minitab or in R. Actually, in RGL too. Two ways. Now this, we actually, let me see what it is. I've got a couple data sets today. Let's look at the cloud data. Cloud data consists of an X and Y's. It's a dew point in the cloud. They sprinkle iodine in the clouds, and then they measure the dew point in the cloud. Okay? And you can think of this as the amount, some kind of, whatever kind of units, the amount of iodine they sprinkle. So we have these 19 measurements. So that's our data. So let me get it in. We'll just split it. We won't look at it first. Okay, so we'll do core statistics. I'm just going to put the data. Okay, there's a summary. Yeah, summaries are great on exams. Okay, I could always give you the summary. No matter whether you're using Minitab or R, I mean, the summary looks about the same. Anyways, there's our estimate. It's highly significant, right? There's the p-value of the one way you've been looking at. So here's our estimate. Actually, the estimate is 1. I forgot. It comes out exactly with 1. Got the data. It's like a coincidence, I think. I hope I got the data right. I think I did. Okay, there's the standard error. T ratio is 13. Now, if you read down here, this part of it says reduction dispersion test. That's the test we just talked about. It has the value 98. So we're certainly going to reject. All right. If you know anything about critical values, means yeah, this is approximately 1. So you're way out. You'll be highly significant too. So the test actually does come out of this. Okay. Okay, that's the first thing I wanted to talk about. The second thing is, we should write the telephone data. We talked about the residuals and box plots of the residuals, but there's one thing to keep in mind in regression. The residuals vary by the variance, the underlying variance of the population, but they also depend on the location in factor space, so the ith case. So if we go back to the residual, you look at the residual, when you do a box plot, it's like the top, okay? You're standardizing that way. But the second way, you didn't bring in anything about location when you did the box plot. So what you want to do is you want to correct the residual with variance and location, okay? And these are called studentized residuals. So we have spine, and downstairs we'll have, I'll just call it the variance. This will depend on location. Okay. I don't know if that's clear or not, but if you're at a different point. Okay, in fact, if you're pretty far out, in fact, the variance will be small. Whereas if you're in the center, the variance is usually large. This is not a complicated illustration. You can't think of an easy way to explain it without getting into a lot of detail. But you can show that this is true. So you have to correct for both underlying variance and location. Okay. Now, the nice thing about studentized residuals, once you've done that, then you can plot those, and you start using these instead of the residuals and residual plots. You get the y hat alone, it's the usual residual plot, okay, except now we have these studentized residuals. And you get something like this. Then you can start putting these lines with plus 2 and minus 2. And you can pick out outliers that way. Okay? So we start using these from time to time, and let's just look at the example I've got here. So let's go back to this. So how do you get the studentized residuals? You just say R student. I'll just call these star. And then you put the fib. So there's the studentized residuals. And then you plot those. And you get to the values. Okay. And then you could just add those lines. It's just, it's add line. Here, the plus minus is. Let's do it. Okay, just go horizontal. See, there's nothing at the top. Because at the bottom, they're going to Any questions on those? We use those from time to time. You can start putting plus or minus 2s in, which is nice, right? Again, one of the most important things about the analysis is to discover the outliers, okay? If you have points that don't belong, you're not going to throw them away, okay? I mean, you're going to be using a robust technique, so it won't really matter. You keep them in. But you still want to discover. Okay, any questions on that? Any questions on the residual plot? What's wrong with the residual plot?
It's quadratic.
Yeah, right, there's something. And that gets us into our steps in that way. Okay, so let's do a few things on multiple injections and we'll come back to this point. It needs something else, right? both the method of least squares and the Wilcox procedure we talked about allows you to easily fit more axes. The only thing you do is go back to this what we have. You just add more axes in. So you could go one more step. So in this case, you're looking at triples, right? Okay, maybe again you're looking at grade point average. Now you have ACT score, but then you also pick up high school percentile, which is usually much, well, for what the things I looked at, high school percentile is much better than most tests. So now and you could have many more. So now you're collecting, in this case you're collecting triples. Okay? So then your model is what? Well, you have an intercept, then you'll have the x1s, right, and the x2s. So that would be the model. And then you're trying to minimize that dispersion function as a function of beta 1 and beta 2. Now, when you just had one x in, you could draw a simple picture, right? And talk about the estimated line. Okay. And if you just have one more x, you still have the geometry. It's just it becomes a solid, right? And you can imagine this room. This room's going to hold our data, and then down here at that corner it's 0, 0, right? And then this is the x1 axis, and then this is the x2 axis. Then you have the y-axis going up. And then your points are triples, okay? So it's like you have a ball, you're this far out on x1 maybe, and then on x2 you're over here, and then you're 2 feet up, and then you put a ball there, that's that data point. And so this room, you have 1,000 data points. You have 1,000 balls floating around, okay? And then you try to slice it with the plane, right? This is going to be the equation of the plane. So you're just picking the best fitting plane through all these data points. It's like you take a big piece of plywood and try to shift it up and down on both axes until you get something simultaneously good. Okay, well now we have 100 predictors on E, 10,000 data points, and then of course it takes care of the room. So that's geometry that you can visualize. But for the model, if you had another x, you would just add it in, and your dispersion function. Oh, in this case, the only thing that changes is the reciprocal. And then you have to compute that, but the computer doesn't care if you have 1x or 100 x's. It just goes ahead and does the algorithm. So you'll get out the estimate. It might take a little bit longer. Actually, you won't see it long. More fit, you can just say, well, let's go through the packages getting more fit. You would have these vectors, right? Y, x1, and x2. And then the fit would be just R fifth. Y wiggle, and then it's x1 plus x2. Okay. And you need to add, say y is in C10, x1 is in C1, x2 is in C2. It's just R into R. C10 is 2 x's, C1 is 6. Okay. Then what about the, you can do a summary. A summary will give you, there'll be a table of coefficients, right? The estimate, standard error, and t-ratio. And these are valid tests in the sense that you can test individual betas to be 0 using that t-ratio. Okay, they're adjusted for everything else. And that's true even, you have to be very careful with R in this. But these t-ratios, we might have a t-ratio for this. Now, where's beta 1? Beta 1 is not in the hypotheses, but it's assumed to be in the model. And this test is adjusted for beta 1. So this t-ratio from beta 2, it is adjusted for beta 1. You know, here's a good here's a good example. We did 2 sample problems. Suppose you have a 2 sample problem where you have like a control and a treatment, right? So you're going to look at the difference between treatment and control. You can do that as a regression problem. I have to go back to this. Let's call them like these moves. So we have, so we have these spies, right? These J's. So we have 2 samples. And we're looking at the chip, right? Well, here's my regression analog. I take Y sub I for B sub. Notation is all this stuff. So there's my 2 samples. That's my vector response to Y. What's my X? A bunch of zeros and some ones. Okay. And if I plot the data, I'll have this. I'll have zeros, right? So here's the first sample. And then here's the second sample. Suppose there's a sort of a big shift. And then my estimate of slope, that's delta n. So I could do a 2 sample problem by regression. We could do that in a second. Okay? Now we have another x in, and we have an adjusted analysis. This is what is meant by an adjusted analysis. I have two samples. I have, it's a clinical study on humans, and there's another variable that's running around I can't control. So I just bring it in as a second x. So it's two treatments. Standard on each cell. And then what? That's blood pressure. Wait. Maybe if I'm doing a study on animals, they'll all be about the same weight. I can't do that with humans. So I just take that into account. So this indicator is my first x, right? It will be zeros and ones. This will be zeros and this will be ones. And then my second x will be the subject's weight. Okay. Now going back to what we started with in this little argument. That's what we did like a month ago, right? Whatever. Today we'd say, okay, we test beta 1 equals 0. Beta 1's delta. I could just fit that. I'll just fit those zeros and ones. But now I have some further information I want to bring into the model. I want to bring it individual weight in. So now my hypothesis becomes what? Beta 1 equals 0, but beta 2 is in the model. See, that would be a difference. If you do this t ratio and this t ratio, you'll probably get much different answers, okay? This t ratio will be adjusted for weight. They often use this in the papers anymore. They talk about the study, the study was adjusted for these variables. So even the papers are writing about it. But that's what they're talking about. They're talking, this is called, actually this is called like an analysis covariance. But and we'll talk more about that later. Okay. You can get some arguments. Not much you can do about it. You want to test it. You really reduce the error. Next time we use it. Okay. Now let's go back to our cloud data then. This is crying for another x, right? I mean, that model is no good whatsoever. And the inference we did, if we did a confidence interval, is waste of time. The inference is no good. If you don't have, if the residual plot doesn't indicate the model is essentially good, or at least it's not bad, then you cannot use the inference. You have to be very careful. So this residual plot is screaming you need a quadratic. So just put one in. So going back to our data, we have y, right? We have x. We need another x, and that'll be x squared. Okay. Sometimes you center the ends. So we'll just do that sweep. And this would be, we'll call it fit 2. See, the table just grows by 1. One's already lines added. X2 is identified. It comes in, it's negative, that makes sense of the residual plot, right? Leading term look negative. There's a standard error, and it's highly significant. And the linear term is still significant too. These can change, all right? I call them the woes of regression coefficients. You can bring something else in and everything changes previously, right? It's adjusted. And then you have to explain that to the client. What happened? Okay, we could look at the residual plot. So we need these 2 types of residuals. So E star 2, how about that? Word line. It's still not that great. I'm always wary of residual plots with poles. Usually it indicates interaction. What would you do?
It seemed to improve it. It didn't go far enough. I'll just try Q.
Yeah. So now I have X cubed. So this would be fit 3. They're all significant. And the signs have stayed the same throughout. And then if we could look at the residual plot here. That's better. Still don't like it that much. At least it's flat, it doesn't have the curve in the last one. It still has that hole. It's certainly much better than the first one, and I think it's better than the second one. The second one still had that curve in it. So we've got rid of the curve. So now I wouldn't feel too bad about using this. Okay, any questions on that? Well, this is like fitting polynomial models. Many years ago when I was a graduate student at Penn State, I took this class one summer where Brian Joyner was the prof. We must have had 6 or 7 of those grad students and staff. And he had students from all over the university in different fields. And stat students just came to class. But those students had to bring in a problem from their area. And then it's like we would break up into groups and we'd visit these problems. It was a very interesting class, but the one guy was from physics. And he had this huge data set. And he wanted to fit this model, and we couldn't get a good model to fit. Finally, we started using polynomial models. And it's like we were a 10-3 polynomial or something. It looked like it was very good fit. And he was very happy with it. Well, it's hard to understand. But the residual plots were horrible because what happens is in polynomial models, you didn't see it in this one, we didn't go far enough, but sines and cosines are just infinite polynomial series. And eventually, if you fit polynomial models, often you see sines and cosines creep into the residual plot. So. Another thing on polynomial models, often you don't know the degree, so there are ways to test for the degree of polynomial. It's similar to what we're doing here. Okay, so let me see, that's the summary, and we talked about residual plots as the same thing. Confidence intervals would be the same, okay, these are the standard errors. Just use a t critical value. The degrees of freedom are it's n minus p. Would be the same if you had a t critical value. It's n minus p. It's a standard error of beta. So that would be your confidence. And you can use that to test this hypothesis, right? This would be adjusted on all other x's. So it would be different if you just fit beta j or xj by itself. And again, you can just do the t ratio to do this, right? You're doing a lot of them, I mean, right? And people will do this. You'll see them get the regression printout, and they'll go down to the t ratios. And each time, each thing they read, they've done a test. So if you have 20 t ratios, nothing could be going on, and you expect they're going to develop response. So you have to be very careful. You have multiple comparison problems. But often you have to do something, and if this is a regression class, we would take a while. We'd stop and pause for a week or two, and talk about model building, right? So if you've taken stat 568, regression class here, you've probably done that. Maybe backwards elimination or forward procedures, stepwise procedures. Okay, that's not part of this course, but that's a often you just have you have too many X's. You want to try to simplify things. Okay? You know, as your model becomes more and more complicated, you begin to violate the KISS principle, which is keep it simple, stupid, right? So you got to be careful. You don't want to violate that too much. So people often go through these. In fact, I just did a consulting thing about a month ago where I eliminated. Not eliminated some. I just used a 20% threshold. So going to the significant alpha 42, I can. Okay. So, make sure I put this in. So confidence intervals. Okay, let's talk about one of the new things, and that is you might want to test you might want to do an overall test. So this is let's just call it general linear models. And there's two ways to do it. From our fit, you could do both ways. Actually, for mini-tab, it's the second way. It's probably easiest. The first way is just to recognize okay, so what you're after is you're testing a specified subset of the betas to 0. I didn't talk about the data set yet. There's 5 P's. I put this data together and I'll talk about it in a second. So they have 5 data. But what I want to test beta 1 equal beta 3 equal beta 5 equal 0. Now, that's not a good way to write it. A good way to write it is this. Beta 1 is going to be 0. Beta 3 is going to be 0. Beta 5 is going to be 0. That's 3 constraints. So in this problem, Q is the number of constraints. Q is equal to 3. Okay? Now, in the first way, we just recognize that the reduced model is dynamic. So the full model is all 5 betas are in, right? And then the reduced model beta 2 and beta 4. Okay. So the full model all have this dispersion, all 5 betas are in. And in the reduced model, it's just beta hat 2 and beta hat 4. Okay? But this is easy to fit, right? Our fit in this case is just going to be y wiggle, then we'll have x1 plus all the way up to x5, right? In the reduced model, it would be r fit, y wiggle, x2 plus x4. So I recognize the reduced model design matrix, right? It's easy. What else would I do? So here's my dispersion in the full model, here's my dispersion on the reduced model, and I just look at the reduction in dispersion. If I add in 3, 1, 3, and 5, so does it improve? So my F test would be the reduced model, right? Minus the full model. Divide that by Q, which is 3. And then I just divide that times 8. And then I reject H1. If that was turned into that critical value, and then 3, and in this case it was, with the intercept is 6 okay? So let me get, this data set. Here's an example. I set this data set up. Okay, the first 5 columns form the design matrix, and the last column is the response, all right? So here's 1, 2, x1, x2, x3, x4, x5, y. I forgot the round y, so let's stop with that. The data are generated from normal errors and variances. Actually 60 squared. But actually under that, there's the true model. But there's a lot of noise in the data. You can just do the one like that. Okay, go with that. It's just. Okay, so there's a full one. This would be. Now, 2 and 4, 4 came in good, 2 didn't. So if you went on T ratios, you'd have the wrong model in a sense. That 5 is better than 2, right? But you have a lot of noise. And then why don't we test that hypotheses? We recognize the design matrix, like the reduced model is just x2 and x4. And you can do it this way if you want to. It's just the original. And then pick out ones 2 and 4. But you could do it other ways too. It's just, that's the 2 columns, right? 26 and 11. So yes, minus 2 is 26 and 11. So I got it in X red, and I just put the reduced model. So this would be fit R for reduced, right? It'll just be R fit of Y wiggle. What is that called? X red. One just doesn't want to come in all. The other one comes in. Okay. Now I want to do the test, right? I want to test to see if I can drop out beta 1, beta 3, and beta 5. I got the full model and the reduced model. And then I just have to put the test together. And there's a function that does it, right? It's called drop test. Drop in dispersion, that's what it's from. It's just hit the full. And of course, pointing to that because you can't, right? You can't reject H naught. Well, actually, you can't reject H naught, right? So H naught might be true. And actually, that, I guess, yeah, actually, the test is the right thing in this case, right? Okay, so this would be, so let me just finish off. Let's go back to this. So again, this problem, the full model of beta 1, beta 2, beta 5 in it, and then H naught is that. So the reduced model is the full model subject to H naught. So it just has beta 2 and beta 4. Okay? And then our test statistic, we get its reduction in dispersion, reduce minus 4, then I'll just do that. Divide that by the number of constraints, which is 3 in this case. And that's how many it's and then it came out to 1.1863. And the p-value is a probability that now with 3 and 30 minus 6 is greater than or equal to 1.1863 is 33. So you tell me. If you were doing model only, you might accept H naught, and then you just have beta 2, beta 4. Okay? Any questions on that? This will be the test we'll be using them from this point on when we do we'll do different tests too. For instance, when we do one way ANOVA, we technically do the Fusco-Wallace test. But we can do drop-in dispersion tests too. Okay. So hopefully you get on to it. And we're going to talk about the second way. We'll talk about the second way on Tuesday. And then I should bring in the old laptop on Tuesday. Because we should revisit Minitab. Minitab actually does it this time.
So that formula, what is tau? Technically,
That's the estimate, that's the analog of sigma m. Which doesn't come out in the printout as part of the code, you know. Let me. Oh yeah, we can get it. I meant to tell, I tried to tell you this yesterday, I didn't have it this week. You can always find out what you can get if you just, yeah, just tell that.
can you switch over please?
You do attributes. You do attributes of the fit. It'll tell you what you can get. And usually you can get these with dollars. Sometimes you can get them with functions. Right? Anyways, you can do fit at metric axis. You can do fit at dollar time. You could also do fit R. Which is epsilon. a minor problem. But anyways, there's time now. Usually you could reduce my estimates. Towns. Try to get some problems.